Hello everyone, welcome to my channel Twinkle Teaches, and here is your friend Twinkle. Hope you all are doing good with your studies. As we are discussing all about topology, here is the next topic in this list, that is a theorem on interior of a set in a topological space. Let X tau is a topological space and A and B are any two random subsets from the set X. Then we have to show that interior of A intersection interior of B is equals to the interior of A intersection B. We have seen in case of union of interior of sets that in union of interior A and interior B is a subset of interior of A union B, which is not the case here, as intersection of interior of two sets A and B is equal to the interior of their intersection. So we will prove this theorem in two parts. As we know, two sets are equal if and only if first set is contained in the another one and the another set is contained in the first one. If A is equals to B, which implies that A is a subset of B and B is a subset of A. We will use this technique or criteria to prove our theorem. In first part, we will show that interior of A intersection interior of B is a subset of interior of A intersection B. This will be our part 1 of the theorem. In another part, we will show that interior of A intersection B is contained in interior of A intersection interior of B. So let us start our first part. As we know, there is a difference between interior point and interior set. If X tau is a topological space and A is any random subset from the set X, then the point X will be known as interior of that set A if there exists an open set U containing that point such that U is open subset of the set A, and interior of a set is the collection or union of all open sets, or you can say it is the largest open set of the set A. So let us come to part 1 of the theorem. The technique we are going to use is we will pick an element from A interior intersection B interior, that is X, and we will show that this point X belongs to interior of A intersection B. So X is a point contained in interior of A intersection interior of B. So we know that by property of intersection that if a point belongs to A intersection B, then that means that point's in A as well as that point is in B also. So X belongs to interior of A and X belongs to interior of B. Then what does it mean? From the definition of interior point, we know that there exists a subset U1 which is contained in tau, that is the topology defined on the set X, and that open set is contained in A also, as X is the interior point of A. Then X belongs to U1 which is a subset of A. It is by the definition of interior point of a set. I have explained this properly in my previous video and link is available in the description box. Similarly, X belongs to B interior, so there exists another subset which is open set also, U2 belonging to tau, and U2 is contained in B. then by definition of interior point, X belongs to U2, which is a subset of B. We are claiming these equations as equation number 1 and equation number 2, and we will use these further. Now understand it pictorially. We have X belongs to U1, which is a subset of A, and X belongs to U2, which is a subset of B. Here is our set A, set B, U1, which is open subset of A, U2, which is open subset of B. Consider this portion, which is drawn with black lines, that is the intersection portion of A and B. Similarly, there is an intersection portion of the open sets U1 and U2, that is colored with blue and red. You can find a black dot under this intersection portion, which is your set U, that is the intersection of U1 and U2. So let we consider U is equals to intersection of U1 and U2. As we know that X belongs to in both U1 and U2, so we pick intersection of them, X will belong to that also. So we can say that X belongs to U, which is a subset of A intersection B, as U1 is a subset of A and U2 is a subset of B, and we have taken intersection of these sets, so X belongs to U, which is a subset of A intersection B. Now, we know that interior of a set is contained in that set. Why we don't say it is equal to that set? This is the only possibility when we have given that set A is open. And here we haven't given such information that either A is open or A is closed. So we are end up with interior of A is contained in the set A. If we say A intersection B is a single set, then interior of A intersection B is a subset of A intersection B. Now we will use this X belongs to U, which is a subset of A intersection B. We have seen this thing previously, and recently we have seen that A intersection B interior is a subset of A intersection B. Combining both of these results, what we get is X belongs to A intersection B interior, as X is contained in this set and this set is contained in this. So X belongs to A intersection B interior. Now we picked a point from the set interior of A intersection interior of B, and we have reached to this point is contained in the set interior of A intersection B, which implies that interior of A intersection interior of B is a subset of interior of A intersection B. So we have proved our first part of the theorem. Let us come to the another part, in which we will show that interior of A intersection B is contained in interior of A intersection interior of B, and this will help us to prove our full theorem. Let us pick a point from interior of A intersection B. We pick X from this set, and we will show that this X belongs to interior of A intersection interior of B. Let us see pictorially how the interior point X looks in the set X. Here X is the set on which topology tau is defined. Here is your set A, here is your set B. See the intersection portion in which the set U is lying. In that you can find a red dot which is showing X, which is the interior point of A intersection B interior. We picked point from A intersection B interior. This means that there exists a open set which is in tau, as we know that tau is the collection of all open sets, and U is a subset of A intersection B. Then X belongs to U, which is a subset of A intersection B. This is by the definition of interior point of a set. If X belongs to U, which is a subset of A intersection B, that means X belongs to A intersection B. Now, X belongs to A and X belongs to B by the definition of intersection of two sets. Again, we have seen before that interior of a set is contained in the set itself. So, interior of A is a subset of A and interior of B is a subset of B. We will use this further. X belongs to A and X belongs to B. Then, this implies that X belongs to A interior and X belongs to B interior, as X is the interior point of the set A and the set B also. So X belongs to intersection of interior of A and interior of B. Now what we have got, we picked a point from the set interior of A intersection B, and we reached at this points belong to intersection of interior of A and interior of B. And both of these results implies that interior of A intersection B is contained in interior of A intersection interior of B. So in part 1 we have seen that intersection of interior of A and interior of B is contained in interior of A intersection B, and in part 2 we have seen interior of A intersection B is contained in interior of A and interior of B. So these both results implies interior of A intersection interior of B is equals to the interior of A intersection B. Hope you all have got this theorem, in which we have proved that intersection of interior of any two randomly picked subset from the supreme set X is equals to the interior of intersection of both the sets, which is not the case in union. As in union, we have proved that interior of A union interior of B is a subset of A union B interior. So both the results are different in case of intersection and in case of union. So if you have any suggestions for me, provide me in the comment section, and if you have any queries, contact me at this email ID. If you need PDF version of my notes, provide me your email ID in the comment section. Don't forget to like and share my videos. Please subscribe and press the bell icon so that you will get notified whenever I post a new video. Stay tuned to my channel if you want to get rid of your fear from topology. Enjoy learning. Thanks for watching.